Let's be honest. We all think we know what gravity is, right? It's the thing that pulls you down. Simple. But what if I told you it's not a force at all? That it actually warps time itself? Today, we're going to dive into why this simple pull we feel is actually one of the biggest and most bizarre contradictions in all of science. And hey, that's not just me saying it. This quote really hits the nail on the head. Gravity isn't some solved problem from a dusty textbook. Nope, it is still one of the greatest unsolved mysteries we have. And the parts we have figured out, well, they are way stranger than any science fiction. All right, let's start with the first massive contradiction. We think of gravity as this ridiculously powerful thing, holding entire galaxies together, but at the exact same time, it's so unbelievably weak, it's almost not there. So which is it? How can it be both? Well, the baffling answer is, it is. Just think about this for a second. Every single time you get up from a chair, your muscles are winning a direct tug-of-war against the entire planet Earth. I'm talking a mass of nearly 6 septillion kilograms. That's a 6 followed by 24 zeros, and your body just overcomes it. Easily. That's how mind-bogglingly weak gravity is on our scale. But then, you flip the script. This same weak force is what keeps our moon from flying off into space. And the moon's gravity, in turn, is strong enough to literally grab hold of our planet's oceans and pull them around, creating the tides. So what is going on here? How can it be so feeble and so dominant all at once? To really get a feel for its weakness, you have to see it next to the other fundamental forces of nature. You've got the strong nuclear force, the stuff that glues atoms together, and electromagnetism, which is behind light and magnets. Then there's the weak nuclear force. And then, way, way down at the bottom, so faint it barely even makes a blip on the chart, that's gravity. It's not even in the same ballpark. It's playing a totally different game. And this right here just brilliantly drives the point home. Just look at that number. Electromagnetism is 10 to the power of 36 times stronger than gravity. That is a 1 with 36 zeros after it. It's a number so huge our brains can't even really process it. And it just shows you how unbelievably flimsy gravity is in comparison. So, how do we solve this puzzle of weak versus strong? Well, the answer comes from Albert Einstein, and it's a wild one. He said gravity isn't a force at all, not like we think of forces. It's not some invisible cosmic rope pulling us down. It's something way weirder and way more profound. It's actually a property of reality itself. Now, you've probably seen that old analogy, right? The bowling ball on a rubber sheet, making a little dip. But even that doesn't quite get it. See, mass doesn't just make a dent on some flat surface. It actually warps the entire three-dimensional fabric of space. And, this is the crucial part, it warps time all around it. So when you drop an apple, it's not being pulled to the Earth. It's just following the straightest possible path through this newly curved space-time. And what happens when you start warping time itself? Well, you get one of the craziest consequences of gravity, something called time dilation. The stronger the gravity, the more space-time gets curved, and the slower time actually moves. Yeah, you heard that right. Gravity literally slows down time. And this is not just some wacky theory. It has real, measurable effects. Gravity is way stronger at the center of the Earth than it is up here on the surface. Because of that, over the last 4.5 billion years, time has been taking just a tiny bit slower down there. And when you add up all those tiny bits, it means our planet's core is about 2.5 years younger than its crust. Just let that sink in for a minute. And this crazy effect is happening everywhere, all the time. Your head is aging just a little bit faster than your feet are. Astronauts zipping around on the space station are aging slower than us. But where it really becomes a big deal is with our technology. The GPS satellites orbiting the Earth are in a weaker gravitational field, which means their clocks run faster than ours. If we didn't constantly correct for this 38 microsecond a day difference, your GPS would be useless, sending you miles off course in less than a day. So, how far does this warping of space-time actually reach? Well, in theory, its influence goes on forever. Your own body is technically warping space-time on the other side of the universe, just a tiny, tiny bit. And this led someone to a pretty brilliant comparison with Star Wars. If you take Obi-Wan Kenobi's description of the Force and just swap out living things for objects with mass, you get a shockingly accurate description of gravity. Okay, so we've got it.
Gravity is the smooth, beautiful curvature of space-time, just like Einstein said. And his theory works perfectly for planets, stars, galaxies, the big stuff. But this leads us straight to the single biggest problem in all of modern physics, the epic clash between our theory for the very big and our theory for the very, very small.
So here's the setup. We have these two incredible theories: general relativity, which perfectly describes gravity and the universe of stars and galaxies, and quantum mechanics, which perfectly describes the bizarre, probability-driven world of tiny particles. The problem? They are completely, utterly incompatible. They just don't play nicely together at all.
And here's the heart of the problem. The other forces, electromagnetism, the strong and weak forces, they can all be broken down into these tiny, discrete little packets of energy called quanta. Think of them like pixels on a screen. But Einstein's gravity is a continuous, smooth fabric. It's like trying to describe a flowing river using only chunky Lego bricks. When you try to apply the weird rules of the quantum world to the smooth fabric of spacetime, the math just breaks. It completely falls apart, spitting out nonsense and infinities.
This brings us to the missing piece of the puzzle. See, if gravity worked like the other forces, it should have a particle that carries it, a hypothetical little guy called the graviton. But after decades and decades of searching, nothing. We have found zero evidence that it actually exists. It's the universe's most wanted and most elusive particle. And that leaves us right here, standing in front of one of the most profound mysteries in the cosmos. Solving this isn't just about figuring out gravity. It's about finding a completely new, unified description of reality itself. So, where do we even go from here? Well, some physicists, like Jonathan Oppenheim, are starting to think we might be asking the wrong question. Instead of trying to force smooth gravity into the chunky quantum world, or vice versa, maybe the real theory of everything is something completely different, a strange hybrid of the two that's neither purely classical nor purely quantum, but some new thing we haven't even imagined yet.
And really, that's the biggest takeaway here. Gravity isn't just the thing that keeps our feet on the ground. It's this deep, fundamental puzzle that forces us to question everything we think we know about space, time, and reality. And if our understanding of something so familiar is still this incomplete, it just leaves you wondering, what else don't we know about the universe?